The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Okay, two presenters. We have Dr. Hoon Kim, who's Assistant Professor in the Department of Civil and Environmental Engineering at the University of Louisville. And he was a postdoctoral research associate at Texas Transportation Institute and at the School of Civil Engineering at Oregon State. Has degrees from Korea University and a PhD from Texas A&M University. And his co-presenter, Jongwon Bae, is department chair and associate professor in civil engineering at California Baptist University. And he was a full-time faculty member at Southern Methodist while completing his PhD. And he has an undergraduate degree from Yonsei University and graduate degrees, including the doctorate from Texas A&M University. And they're going to speak about the probabilistic model for predicting early age creep deformation of SCC.
Thank you for introducing us, Dr. Bronx. And I'm very moved because I was here, not this convention center, but 7 years ago. I was the same session for presenting my PhD work. But now I'm presenting the new topic with my PhD works and continuing that effort now. And then now I'm going to present the probabilistic model for predicting early age creep deformation of SCC, but particularly for applying to the precast precursors members. And then I'm presenting the first part of the presentation, and the next part will be presented by my co-author, Dr. Bai. In the outline of this presentation, I will present about the background of my research and our research and motivation and objectives, and then what kind of data I collected and I used for develop the model, probabilistic model in this study. And this is ongoing research, is not complete yet, so we are going to present the preliminary results and finally summarize and conclusion of this research. As a background, so why we need to concentrate on the creep deformation, I would say one of the big example is that the bridge failure in the Palau, as my pronunciation may be correct, but the bridge is crossing the two islands. And it is a pre-stressed concrete bridge, but it's not precast members. It was built in 1978, and then what we observed that after about 16, 17 years is that midspan, the deflection is about 1.2 meters. It's quite visible. So that people repair that midspan and compensating the deflection, but the deflection is not fixed and getting worse. And finally, excessive pre-stress loss and bridge failure occurs in 1996. So what I'm seeing now is that, okay, the creep is kind of what we consider as a serviceability and predicting some pre-stress losses and long-term deflection, but it's not creep, it's not as a serviceability now. It's kind of an impact on our structural integrity, so and such as a failure. So we need a better prediction for creep, and nowadays we are using the very modern concrete, high-performance concrete for precast pre-stress concrete member, and also including the self-consolidating concrete is quite widely used now. But still, I believe the database is quite limited for predicting the creep data. So we are trying to collect as many as we can, and then try to propose the new model, better prediction for creep deformation, and then long-term behavior of the bridge structures. So it's quite a basic for all of you, but I try to introduce some basic concept of creep coefficient. This is a quite creep coefficient is now we are used in the bridge design, AASHTO design code or other similar design code. And then creep coefficient is when you see here is the ratio between the creep strain and over the strain due to the instantaneous stress, constant stress, sigma sub A. But this is easy to apply in the design equation, but we are focusing on our model, how we can better prediction model with some fundamental information. Is that the strain over here? Is the summation of the creep strain plus elastic strain with the shrinkage strain, and then temperature strain. So these four terms are summed up together, and then we can get some total strain of the bridges. But when we're looking at these two terms, when you add up together, and then I will introduce the compliance function, is that summation of the creep strain and elastic strain all together as a function of time, and then when we apply the stress at the time t prime, and we do this stress, constant stress. So we are now seeing, okay, the elastic strain and with the creep strain can be summed together, and then we can see how those things impact on our creep prediction model. So we are going to use the compliance function after this point, and then we also looking at what is the relationship with the existing creep coefficient in the design equation is over here, and then creep compliance function is equal to the creep coefficient plus 1 divided by elastic modulus at the time of loading. So this relationship we are going to use to predict better creep coefficient, but our model is calibrated based on the compliance function. So that usually we know that the Bajant model, D3 model, which is available now, and then this is basically based on the compliance function. And then we try to capture better intrinsic parameters and extrinsic parameters for predicting the creep. And then when we see what is the difference between intrinsic parameters and extrinsic parameters, I would say intrinsic parameters is based on the material proportions, like a water-cement ratio and water-to-binder ratio, aggregate type or stiffness, different type of aggregate, and cement type, and fine total aggregate ratio, and also slump flow or slump we use as intrinsic parameters for predicting the creep. So many existing models actually including the many intrinsic parameters. But I would say that in current Ashton model, it's focusing on the extrinsic parameters because this parameter is more easy to apply for the designing the bridge structures. So we are using now is the age of the first loading, like when we release the pre-stress strands, or when we apply the dead load and live load, and such as. And the age of the casting is that the life of the bridge structures, and then we can predict the deformation or creep deformation and then deflection. And then 28 days strength and the volume to surface ratio is that the dimension of the bridge girders, and elastic modulus at 28 days. And then something like relative humidity or temperature can be also included as eccentric parameters. We try to modify the Ashton design code. Dr. Bai will present further. But if we include some intrinsic parameters, which we have some data is available, then we can have a better prediction model. So that's the starting point of our research. And then this is basically, I try to show that how the Ashton code look like. And the pre-coefficient is that summation is equal to 1.9 is some correction factor with considering the humidity factor, case of HC, and case of V sub S, considering the volume to surface ratio, and case of F is that the effect of concrete strength, and case of TD is that the impact of the concrete strength. All of these four terms is expressed as this long equation, but actually when you see it here is that all parameters are based on the extrinsic parameters. So this is when I summarize our motivation, and we understand that we are using the high performance concrete, including SCC and then some modern conventional concrete, but still we are not sure about the robustness and then predictability of the existing model. And also existing model is based on a lot of the database, but still is quite a deterministic model. And so we needed to improve the robustness, and so that's why we are going to start this research. And then first step of this research is, okay, what kind of intrinsic parameters are important for predicting the creep? So we are trying to identify the important parameters from the intrinsic parameters, and then with that, we improved our model as a probabilistic prediction models. So that's my motivational objectives. And next presentation will be Dr. Bai after this. And then let me summarize our databases. We have about 4,000 database from the 5 different researches. We're still collecting the data, but majority of the data is for the SCC application. 41 batches, a little misprinting about the application SCC, but actually 41 batches including high performance concrete SCC and high performance concrete, conventional concrete. And then 36 batches is from SCC and 17 is about from the conventional concrete batches. This is the mean value is 555 when we apply the creep loading. And this is the water binder ratio and binder aggregate ratio is here. And then 0.75 is that the day when creep loading is applied. It's quite simulating the when we release the pre-stress strength and 7 days and 20 days. And the elastic modulus is ranges over here, and then age of loading is 0 to the 365 days. Not only taking the data at the end of the creep, we actually try to fitting our model to entire lifetime of a creep deformation. So Dr. Bai will present why this age of the loading is quite important in our prediction model. So I will transfer this slide to the Dr. Bai. And
good afternoon. My name is Jong Bae. I'm from California Baptist University, and this is the first time for me to make a presentation at the ACI convention, so it's kind of interesting. So I'd like to continue to talk about the probabilistic model development. As Dr. Kim mentioned that we currently have an Ashton model, which is widely used to predict the creep deformation, but some limitations are there. And then also, this model is developed mostly based on the conventional concrete. So we have to think about how accurate this model is predicting the creep deformation for self-consolidating concrete and high-performance concrete. So that's one of the objectives of this study. So we started from the current Ashton model, 2013, and add two parameters, water to binder ratio and the binder to aggregate ratio, which are two parameters among the intrinsic parameter, as Dr. Kim mentioned earlier. And then we added those two parameters into the current Ashton model, and then developed the proposed model based on the probabilistic manner. So I used the Bayesian updating approach to estimate the unknown parameters in the models. I'm going to show you what the model look like and how those parameters look like. So this is the proposed prediction model, quite kind of busy, but as you can see in this large bracket, everything up to this point is the phi model, the current Ashton model. And because of the conversion from phi to j, the compliance function, we have to have phi plus 1 divided by Young's modulus E term here. And the reason that we transform the data into the log normal space is the log transformation usually kind of to reduce the nonlinearity so that we can easily make up the linear model to fit the data points. So because of that, the Young's modulus is in another term with another parameter. So the total 6 unknown parameters, including this constant theta 1, and here we have 2 additional terms in addition to the phi, the current Ashton model here. So we have theta 2, theta 3, and theta 4 is the coefficient in front of mostly the current Ashton model, and theta 5. And here the sigma times epsilon, that's not stress and strain. This is the sigma used in the statistics, the standard deviation of the model. So this, I can say this is the error term. So we run the analysis using the Markov chain Monte Carlo simulation. So basically, it started with a certain initial point, and then the algorithm find out the optimum set of the parameters, theta 1 through theta 5, including the sigma. And the analysis is terminated when they satisfy the convergence criteria. We use the Gewick convergence criteria, which compare the first 10% of the data points and then last 50%, compare the mean value. If the difference is less than 5%, the analysis is terminated. So this is the series of values of those parameters, theta 1 through theta 6 is basically the sigma. And these are the PDF of those parameters. And this is the result. And as Dr. Kim said, this is an ongoing project, so we are planning to improve our model in the future when we have more data available. But as you can see, this is a relationship between the predicted compliance function J versus the measured compliance function J. And the red dots, the circles are the data points based on this relationship from the Ashton model. And these blue cross dots are based on our proposed model. So in general, I was kind of surprised that the current Ashton model is pretty working good in overall. There's some reason that, by the way, these red dotted lines are the plus minus 50% bounds, which AASHTO currently allows to have. So the AASHTO current model is pretty good, except these data points. There are certain points are out of the bounds. So when I zoom in these reasons, and one of the reasons is because we're looking for the early age crypt deformation. So as you can see, when you compare these two models, the reds are from the AASHTO and the blues are from our proposed model. Our blue model is a little bit kind of close to the 1-1 line, and then most of the data are within the 50% boundaries, while these red dots, especially these points, are out of the bounds, which is allowed by the AASHTO currently. So this is the current results, and I'm going to summarize what we have done. So the existing model to predict the crypt deformation are not fully verified for the high performance concrete, so that was one of the motivations that we started this study. And important parameters affecting the crypt deformation, especially for the intrinsic parameters, are added in the proposed model. So the proposed prediction model was based on the AASHTO and add those two parameters. Using the Markov chain Monte Carlo simulation, we updated those unknown, the posterior statistics for the unknown parameters, and then proposed model provides more accurate predictions, especially for the early portion of the crypt deformation. So in the future, crypt experimental, the plans are established, so we're planning to collect more data. The California Baptist University, I work with two of my student workers during the summer. We create testing frame. So we are going to cast a concrete specimen and then put it into the frame, really measure the crypt deformation over time. So that's one plan in the future. And so that the more test results and observations will be added to develop and update the parameters to have more robust models covering the various types of high performance. Thank you very much.